Good morning, good afternoon, good evening to all attendees. We are so glad that you are here and have made it into the Zoom and that we are able to still have this tutorial today. I'm going to pass it over to Nate Lindsey, who's at Stanford, and he will be giving you a bit of an overview of what we're going to be doing today and the logistics of the meeting. So take away, Nate.
Thanks, Kasey. So welcome everyone to day 2 of the 2020 DAS workshop and tutorial. This is going to be more of the tutorial day. And I just wanted to kind of start by, showing the team again. That's the large team here. Kasey's been kind of helping us get organized and doing so much support. But we kind of, Scott and Dante did a great job, I thought, on day 1. And Herb, discussing pieces of DAS and DAS research and kind of the background of where this DAS technology has come from. And today, Eileen and I will be working on kind of more hands-on training with some Jupyter notebooks that hopefully you might have gotten a chance to look at. And so we thought we'd take today to kind of just this first half hour, maybe 40 minutes, is going to be looking at kind of just the overarching view of what we're doing here, and also a bit about the measurement method. So day 1 was a webinar. Day 2 and 3 are going to be a general meeting. That is, the Zoom format will be like this. So please mute your mic and turn off your camera. And if you need to, get in touch with us or talk to someone about the particular coding issues that you might be having, or particular issues with Brady Hot Springs or Forge data sets, you can use the Slack environment. You can also use the Zoom chat, which is here. And then when we're going to be going into what are called breakout rooms, groups of smaller numbers, please at that point turn on your mic and turn on your video and introduce yourself and kind of be free to talk like a normal meeting at that point. But when we return to this meeting room, please mute your microphone and turn off your video. So again, if you have technical difficulties, get in touch in one of the many ways that we have. And so there are a number of guides, and you'll see that in the chat function. They've been designated, hopefully themselves, as guides. But if you see any of these people in the room, in your breakout groups or whatever, these are DAS experts, graduate students and postdocs. So please kind of reach out to them for support if you're having trouble with the DAS concepts. Now, these aren't necessarily Python experts or are not necessarily developers of the Jupyter notebooks. But they kind of do know a lot about DAS, so they should be able to support in a technical way the content of what we're going through. So just to recap a little bit about day 1, we had 2 talks that kind of bookended 2 talks that were not necessarily on DAS explicitly. So we had Lati talking about this kind of experiment in Iceland, looking at some DAS observations of the telecom array. And we had Richard talking about earthquake early warning, and Carrie Ann discussing a lot of the machine learning aspects of kind of geophysics today and where that might go with DAS in the future. And then we had Herb talking about kind of field installation and early DAS experiments, field trials, comparing to geophones and this kind of a thing. So I want you to kind of, from day 1, be thinking about interacting in a couple other ways besides just this synchronous time. So you can be adding questions at any time to the FAQ page here. And we'll be covering this on day 3. We'll take some time in a breakout group to kind of begin to answer these FAQs. And this will be working as kind of a community resource in the future, kind of a referenceable FAQ page. The other thing is there are these lightning talks on day 3, so we'll start day 3 with these lightning talks. So if you're interested in sharing something about your DAS research in a short 2-minute video, or short 2-minute talk here in the workshop on day 3, please complete this form and then email 1 to 3 slides to this email here. And do that by this weekend so that we can get organized for next week. Okay, so just a little bit about why this tutorial is in the way that we're doing it today for day 2. some motivation. DAS has a wide range of users. You can envision maybe 5-10 years down the road, there are civil engineers, there are kind of cryosphere scientists, or seismologists, or oceanographers, all wanting to use DAS. So DAS is this incredibly flexible tool, right, that works in kind of exploration geophysics context. But because we're able to use telecom arrays too, we can go into very interesting areas like glaciers and offshore. And so what that means is that we have a large community. So when we think about issues today, this is the kind of a Venn diagram of sorts of the state of the DAS community that Eileen Martin put together. So we have this outreach and workforce problem, which is very different than a lot of the problems that are talked about in DAS. So a lot of times we're talking about data issues or instrumentation issues about instrument response, for example. But we also have this outreach issue, which is that the community is not so necessarily expert in array signal processing or working in DAS in particular. So we see DAS talks in AGU and SSA and other areas, but actually putting the skills out there is not quite been done yet. So this is kind of where we're going to be focusing on today, is kind of providing some of the training and background for this. So if day one was kind of on building interdisciplinary community and discussing kind of some of the research opportunities or recent research, day two today is really going to be on kind of focusing on public data sets that are available, some fundamental concepts, and putting out a starter pack of tools that will allow us to kind of get going with looking at some of these public data sets that are already out and available. And it also kind of hopefully drum up some interest in kind of collaborating through the Slack channel maybe in the future on kind of using these tools, expanding these tools, and continuing to kind of work on these data sets. So I want to kind of emphasize that this is really a starting point, and that we only have a few hours today to tour the notebooks. So continue working. Don't treat this as kind of just the only time that you have to work on these notebooks. They will be available. So we've put together a page actually where you can find available DAS data sets. And that page is here. So today we'll only be looking at 2 of those. But if you want to look at this link, and maybe we'll share this in the Slack channel later, but you can go in and actually see some of these different DAS data sets that are available. And these are either been archived formally with a DOI for a publication, or they're kind of a snippet of an earthquake wave field or a noise recording at some location. And so they kind of range from kilobytes to terabytes of data. And we'll be looking at two of these examples today, but you could apply the same tools that we're looking at to any of these different data sets just by going and finding them. And so the hope is that we can make the DAS, even though there is this kind of data issue with archiving data is difficult when the data sets are massive, but we kind of could get started at least already with looking at some of the data that's been collected. Okay, so let's take 20 minutes and talk about the measurement principle here. I think there have been a lot of questions on day one and also since day one, and I'll also kind of looking through the FAQ page on what exactly we're measuring. And Lottie did a great job of explaining it. Herb did a good job of explaining it. And so I'm going to take another cut at this in the hope that kind of you see many different perspectives about what we're actually looking at when we think about recording data with DAS. So we kind of all have this understanding of how fiber optics work, right? Total internal reflection conducts light at a given angle down the core of a single mode fiber. We use single mode fiber in DAS. And that just means that one wavelength is allowed to conduct down this core, which is kind of the thickness of a human hair. And it's done because there's a difference in index of refraction. So the type of material inside the fiber versus outside is different. And that allows, just like Snell's law, it allows conduction of this light. So that's how fiber optics conduct light. That's how the internet is now transmitted across the globe with these long telecom fibers. There's also scattering, and telecom companies are aware of this, right? So you can see in this kind of analog, this is a piece of plastic, but you can imagine it being a core of a single mode fiber. you can see the light moving down the fiber, but you can also see some of the light is coming back up into the camera lens, right? Some of it is scattering at each point along this, of this quote unquote fiber. So most of the light continues down its path, but some light scatters. And that's Rayleigh scattering. So Rayleigh scattering is scattering at the incident wavelength. It's at the same, the incident photon is the same energy as the reflected photon, the redirected photon. And so backscattering is what DAS uses, and that's light that returns back to the source, the interrogator, at one end of the cable. That's what's meant by Rayleigh backscattering. So we can actually estimate, we're not adding anything to the cable here, and this should be fairly clear at this point from day one that DAS is really just using these scatterers in standard fiber. And this slide is basically just doing a little calculation to say that basically based on the energy of the photons that we're sending in with DAS and the Rayleigh scattering that we know from cable kind of standards, fiber cable standards. For example, the loss in a cable is about 0.15 dB per kilometer. We can actually estimate how many scatterers, Rayleigh scatterers, are embedded in the glass of the cable. And it turns out to be many, right? Thousands per meter. So that inherent scattering principle is what's used in DAS. So you can see here, I'm color coding. This is the core of an index core of a single mode fiber. And so at each place here, the color coding means that there's a change in density or a change in index of refraction. So some sort of imperfection that leads to scattering when we send in a pulse of light. So again, most of the light continues down the fiber, but some of it is scattered at each position of these changes in index of refraction. And so DAS is going to use optical time domain reflectometry, or OTDR, to basically account for where these scatterers are. We're not actually going to locate any scatterers. That's not necessary. Really, the point is that we send in a pulse of light into a fiber. We record the backscattered energy from every point, and then we apply the fact that we know the speed of light in glass to assume that there's a two-way travel time, and we can actually transform that backscattering profile in time, a time series, into one in space. So we can account for where that light has scattered from with the simple assumption of the speed of light in glass. So we very carefully record that time series of the backscattering, and then we transform that into space. So I think that it's good to think about DAS in two different ways. And I think that we've really been focused very much, you give a geophysicist an instrument and they think about it like a geophysical instrument, right? So DAS for the last many years has been thought about in seismology as this geophysical instrument. And what do we think about when we think about geophysics? Well, we think about geophones, right? So, how is a DAS a geophone is the kind of easiest way to conceptualize of DAS. It's just this long string of geophones, right? So in the geophysicist perspective, that can kind of be thought of like this. So we have a fiber and we have a couple geophones, and they're separated by what's called the gauge length. So this might be 10 meters, or it might be even less, 1 meter. And we shift this gauge length down the whole fiber, and we locate it. Its midpoint would be called the channel. So the channel position, Z in this case, is here, and the gauge length represents the spatial resolution across which the strain is actually going to be measured at each time step. And then you can imagine that we can shift this gauge length, this DZ, we can shift this by increments that are very small, right? So our channel spacing can be 1 meter, but we're just shifting this 10-meter gauge length, just 1 meter as we kind of slide the gauge length down. So this is the difference between gauge length and channel. So in a little bit more context here, the geophysicist perspective was kind of described a couple of years ago by Tom Daly. So thinking about what was actually being recorded at each position, well, it's displacement at a let's say it's it's a geophone will record velocity, but let's just say that for the sake of argument that we're recording the displacement at this position. That's U, so U of Z. So the kind of description of DAS is actually a kind of change in the displacement in space. So the difference between the displacement at this point to this point. And then that same difference, so the difference in these two positions of displacement through time. So we'd record the difference of displacement at one time, and then the difference of displacement at the next time, and we difference those. And that leads to kind of description of strain rate of the measurement. So du dz would be strain, and then we take the time difference of that, and that would be the strain rate. So this is, you can swap these operators, and then you have this kind of gradient of velocity too. So what that means is that, we can actually relate DAS to this difference of two velocity sensors by thinking about the measurement here. Now this is a Silixa, to use a kind of vendor term, this would be the strain rate or the Silixa type of a recording. Actually, this figure is kind of recorded from a paper that used Silixa data. But this allows us to actually do a lot of things, right? If we kind of brush aside the fact that we can also record strain, this is from Herb Wang's presentation. He showed that by recording with seismometer data on the ends of a couple of gauges of DAS, you could very clearly represent the waveform, right? This is a difference of geophones, and then the DAS trace next to it, right? And we've kind of described on the previous page that these things are comparable. And so from the geophysicist perspective, I think it's very clear that this kind of this idea of DAS works in this for the phase information here, right? So these are very clearly lined up waveforms. But there's also some important impacts to this also. So thinking about recording strain instead of particle velocity means that there's this azimuthal trade-off. So if a wave is coming in like this and it's a P wave, that would be like a longitudinal wave here, then the blue shows what a geophone would record. It's kind of a cosine kind of fall off. So at 45 degrees, if the wave was coming in at 45 degrees instead of 0, the amount of energy recorded would be 75 or 70%. But with DAS, it's cosine squared type fall off. So at 45 degrees, we're only going to record about 50% of the energy there. And it's even more different for transverse waves, so S waves. So these type of impacts are just because we're recording strain instead of particle velocity. And so while we could convert this to a geophone, there's really important, fundamental recording differences. And I think, this perspective is great, and it has allowed us to do a lot of different geophysics with DAS. But I think that some of the FAQs on DAS that were collected over the last few days really kind of begin to break down this perspective. So this question, like what really limits the low frequency DC response of DAS? When you begin to look at quasi-static strain, how do you difference geophones to look at that? What does that actually mean when you're differencing two velocity sensors when the deformation is static? Another question, kind of thinking about clipping, what does it mean when you're clipping an interferometric measurement? So this optical measurement, what does it actually mean to clip that data? It's not the same as a voltage sensor. Another question that comes up a lot, and I get this question a lot, is when we compare different DAS systems, there are trade-offs, right? So if we record strain rate versus strain, or we recorded a given sampling rate, that's possible with some instruments and not at others. What are the trade-offs here? And kind of a kind of moreover statement on that is, what are the limitations of interpreting DAS recordings coming out of different studies? And I think that in order to understand, especially these last two, we really have to think about this in terms of a photonic instrument, kind of also. So kind of taking that for a couple minutes, we can think about what is actually being recorded here photonically now. So if 0 represents the position of the instrument, then this would be like the backscattering, right? The Rayleigh backscattering profile that I talked about as a function of distance, kilometers, in this case, 20 kilometers. So we send in a pulse that would be like the blue in the background. There's a blue trace here in the background from Zhongwen Zhan's recent review paper. showing the first laser pulse in blue, and then after some perturbation in this section in gray, you can see that there's this red is shifted in this section. And so if we difference these two laser Rayleigh backscattering profiles, we get this, right? So this kind of change that would be related to some sort of phase difference in this section of the cable. And so I kind of put this equation down here to represent what's actually being done photonically as a measurement of phase change. So optical phase change is related to strain in the direction of the cable by the wavelength of the light, the gauge length choice, so like 10 meters, the index of refraction of the glass, and Pockels coefficient, which describes the material properties of the glass. So you can very clearly represent an experiment like this. So if we measured a change in phase at a position here, we would know exactly that it's approximately 11.6 nanostrain per radian of phase change. So this is a photonic description of the same method that we were talking about before, but kind of a little bit more detail on the photonic side. So, then the question comes up, okay, so, I hear that DAS can record strain rate or strain. Why is that? Well, that has to do with the photonic setup, right? So if we record optical phase change, so delta phi, then that would be related to a strain. But if we record the time derivative of delta phi, then that would be related to a strain rate. Right? So thinking about that, I like to think about that like this. So this picture comes out of a photonics review paper by Masudi and Newson. And again, thinking about it like how Zhang Wen drew the picture in his review paper, here's the first pulse experiment, right? Here's the Rayleigh backscattering profile from the first pulse as a function of distance. And this is called the fast axis. So in the first pulse, light returns from every point in the cable. And it does that in a very fast time scale, right? Like nanoseconds to microseconds kind of time scale, right? The speed of light in glass is about 2/3 of c. And so we can do this axis here is called the fast axis. Whereas if we repeat the pulse experiment, the next laser pulse, right, that goes into the fiber might go in, 1,000th of a second later. So we might sample this cable at 1,000 laser pulses per second. And so the second pulse actually is very slow compared to this first, the time it takes for all the light to return is very fast, microseconds. And this axis, this kind of slower axis of laser pulse repetition is maybe on the millisecond to microsecond time scale. But then again, when we send in this second laser pulse a 1,000th of a second later, light returns from every point in the cable, right? Again, along the fast axis. And the point here is that when we think about this photonically, we can actually make a measurement. What are we actually measuring here? We're measuring the change in phase, right? And a change in phase is just a shift of two sine waves, right? We're just measuring that delta phi between two samples. Well, if we set up the optic system in one way, we're actually going to measure the delta phi, the same delta phi, between two ends of our gauge length. That would be like method A here. So some optic setup, let's just take for granted that some optical setup allows us to measure delta phi along the fast axis, while a different optical setup allows us to measure delta phi between pulses. So that delta phi, so if there's some seismic wave that comes into our cable between pulse 1 and pulse 2, we're going to measure delta phi here very quickly. And so that's just going to be a measurement of delta phi, right, at each time step. So that's proportional to strain. But the measurement in this direction is going to be delta phi divided by the time it took between pulse 1 and pulse 2. Because that's a little bit slower, we need to actually account for that time. And so this requires a delta phi change per time, per dt. And that leads to a delta phi rate or a phase rate in this axis. So that's why we might have strain rate versus strain. So taking a step back, I think in DAS, we've had many different observations at this point with DAS data sets all over the world. In Pasadena, they've recorded floats in the Rose Parade this past January. So these are different bands in blue here, and they're kind of the noise in the 1 to 10 hertz band. They also recorded longer period energy related to the deformation of the roadbed. There's been kind of surface orbital sweeps like what Herb described actually with the mini vibe. And this kind of in tens of hertz up to maybe 100 hertz. And even in the oil and gas industry, they're going to use seismic sources that are even higher frequency, right? Hundreds of hertz. Eileen Martin, looking at the Stanford DAS array, saw this kind of day-night and also weekday-weekend kind of variability in the noise in this kind of 0 to 20 hertz band. And so Thomas Coleman and Matt Becker at Cal State Long Beach did this experiment where they kind of drove the fiber at a given frequency that was the same frequency as the tide, the earth tide. So thousands of seconds, tens of thousands of seconds. And they saw the same response of a fiber. So this suggests that there's a frequency response of DAS is incredibly broadband, right? It's kind of down to the tidal band. That's kind of one of the most broad band instruments that we have. And so when we think about even teleseismic recording, right? So we can certainly get tens of seconds to be able to look into the mantle with these kind of teleseismic phases. So the question here is so if we can kind of clarify that DAS does have frequency response at many different frequencies, what is the instrument response? So what is the kind of amplitude variability at these different frequencies? And this is kind of just wrapping up. I think that the kind of instrument response should be thought of maybe as from the geophysicist perspective, right? We're recording a wave field with an instrument, and we want to know how to remove the effect of that instrument. That's what instrument response, that's why we're driving towards this description of instrument response. And we're not there yet. We don't really understand instrument response in the field, but in theory, we should have this, this type of response. So it should be flat at DC, kind of DC meaning quasi-static type deformations of long periods, but then have this notch at higher frequencies or shorter periods, related to basically the fact that if we have a wavelength whose wavelength is exactly the gauge length in an apparent velocity sense, then there's zero strain applied to that gauge length. And so we're going to have this notch of zero amplitude at that position. While in phase, it should be flat. So other geophones, for example, or nodal seismometers, are only going to have short period response, like the Z1 node. The DAS should have this very long period response. And I just wanted to show these two examples. We did this experiment where we put out a broadband CMG3T sensor next to a DAS, so it'd be a kind of standard broadband sensor, and compared teleseisms and microseisms. And we see this kind of response, flat phase response. And then the amplitude response has this kind of flat response from 10 to 100 seconds, but then goes up at shorter periods. So higher frequencies do show this kind of increased amplitude response. And the thought is that this is related to coupling of the cable. And there's been additional work kind of expanding on this many orders of magnitude actually in terms of the frequency response by colleague Patrick Pates at ETH in Zurich. So this is kind of, I'm sorry, the x-axis is flipped in this case. So this is higher frequencies or shorter periods is on this right-hand side, and longer periods are on this left-hand side. But amplitude and phase response here, looking at hydraulic injections, earthquakes, teleseisms, and also local earthquakes, vibra-sized controlled source, and also an ice quake. They see this in terms of the phase response, it all looks relatively flat. So similar to what we're finding in Sacramento, California with this experiment. But then the amplitude response looks to be kind of changing and actually increased like we found at short periods, but decreased at longer periods. And so these two experiments kind of show they take the theory to the field, right? And we see this kind of potentially, we're both kind of thinking about this in terms of coupling. Maybe the fact that the jacket or the conduit adds some sort of coupling issue on the amplitude response. So to kind of summarize here, and I think it's helpful to maybe just show, this kind of leave this last slide and, discuss kind of what we're thinking about in terms of this measurement. In terms of these three principles allow us to do the DAS methodology, total internal reflection, Rayleigh backscattering, and the OTDR method. So these are the basis of DAS. And DAS can be thought of as this geophysical method or a kind of a photonic method. And the photonic principles, I think, are going to become more and more important as we dig into the details of DAS in the next few years. And instrument response does require many more field and laboratory calibration experiments. So if there's folks that are interested in kind of jumping on board with this, we'd be very interested to see what you find. Preliminary results do indicate this kind of flat response and coupling effects in terms of the amplitude. So I'll leave it there. I think we're going to take questions for a minute, maybe, Eileen?
Yeah, I'll moderate questions. It looks like there was one from Lizzie Klein in the chat, but then Herb Wang has answered that one, which is great, thanks. And then there's another one here. So if you all have questions, put them into the chat. We just have time for one or two. So from John Hole, is delta phi measured optically or digitally? That is, when does digitization happen?
So I think the delta phi measurement is going to be measured, it's an interferometer. So we can set that up to actually measure that optically and then digitize the signal. And then we have to deal with kind of unwrapping that signal because we're going to limit our digitization. But there are methods there are optical setups that are actually recording it digitally and then kind of convolving the two optical signals. So to answer your question, both, and it depends on which instrument you use.
Great. Any last questions? It looks like here's another one from Min Chen. The coupling effect seems to only happen at periods shorter than 10 seconds. Does that mean the waveforms at 10 seconds and longer can be reliably retrieved and comparable to broadband instruments?
So again, these are the kind of the first two experiments testing this. So I don't want to say that it's possible in every case that we should just take this and run with it. We need a lot more calibration, but it was encouraging, I think, it was encouraging that it's at least flatter, this kind of, plot showing that it is flatter at longer periods. So more work to be done there, I think.
All right, and we've got a couple more questions in the text chat. So I'm just going to take one of these real fast, and then we're going to go into breakout rooms after that, just to keep us on schedule. So from Yuri Staravot, what is the estimation of DAS dynamic range?
I haven't actually seen a number on this, although I think they're beginning to be discussed. The top end would be related to maybe some the kind of amount, the degree to which you can unwrap your phase, and the kind of low end of that dynamic range is going to be related to the noise floor of the instrument. But I haven't actually seen numbers on that, so I don't want to speculate on that.
Great, thanks very much, Nate, for that overview.